Welcome back to the computer lessons.
Touchscreens represent the ultimate fusion of display and input technology, creating a seamless interface that eliminates the need for separate physical controllers. This direct manipulation of digital content relies on complex sensors embedded within the screen layers to detect precise coordinates. Computing has moved from abstract pointers to immediate tactile interaction. To understand how a sheet of glass detects a finger, we must first look at the physics of the human body. Our skin is a complex organic conductor, capable of holding an electrical charge and disrupting local fields. Every touch is essentially an electrical event that the hardware must interpret. The history of the interface began in 1965 with E.A. Johnson, who developed the first capacitive touch sensor for air traffic control systems. While primitive, this invention proved that software could be controlled by human touch. It laid the foundational logic for the multi-touch era we experience today. The most common technology is the resistive touchscreen, which functions based on mechanical pressure rather than electrical properties. It consists of IKE flexible layers coated with conductive material, separated by a thin gap. When you press down, you physically force these IKE conductive sheets to touch. To prevent these layers from touching prematurely, engineers use microscopic spacer dots to maintain a uniform air gap across the surface. These spacers are nearly invisible to the eye, ensuring optical clarity while maintaining the mechanical integrity of the device. They act as the invisible insulation of the screen. When the layers connect, they complete a circuit, creating a voltage gradient across the horizontal and vertical axes of the panel. The controller measures the resistance at the point of contact to calculate the exact X and Y coordinates. This analog signal is then converted into digital data. Resistive screens are incredibly rugged and can be operated with any object, including gloved hands or plastic pens. However, they lack multi-touch capabilities and suffer from poor clarity because the multiple layers reduce brightness. They are most commonly found in industrial machines, ATMs, and medical equipment. Modern smartphones utilize the more advanced capacitive technology, which relies on the electrical properties of the human finger. Instead of moving parts, these screens use an electrical field that projects through the glass. When a finger approaches, it draws a tiny amount of charge from the surface. The magic material that makes this possible is Indium Tin Oxide, or ITO. This unique substance is both optically transparent and electrically conductive, allowing it to act as a sensor without blocking the screen. It is etched onto the glass in a complex microscopic grid pattern. Early capacitive screens were surface capacitive, detecting touch by measuring the change in current from the four corners of the panel. While effective for single-point interaction, they were vulnerable to noise. Modern devices use projective capacitive technology, which is the current industry standard for high-performance mobile devices. Projective capacitive screens utilize an X and Y grid of conductive traces etched into a single dielectric layer. This grid creates thousands of tiny sensing nodes across the surface, each capable of detecting a local change in capacitance. This high resolution allows for the sub-millimeter precision required for typing. The core sensing mechanism is mutual capacitance, where the controller tracks the interaction between the horizontal and vertical grid lines. When a finger touches the intersection, it reduces the mutual capacitance at that node. The system scans the entire grid thousands of times per second. Some screens also utilize self-capacitance, where each individual electrode in the grid is measured independently against the ground. This method provides a stronger signal for single-touch events, and is often used for detecting a finger before it even touches the glass. It enables features like hover touch in some advanced smartphones. The top layer of a modern touchscreen is typically chemically strengthened tempered glass, which provides structural protection for the sensors. This glass must be perfectly uniform to ensure the projected electrical field remains predictable across the entire surface. Manufacturers use ion exchange processes to create a surface that resists scratches. To achieve a fluid experience, the touchscreen controller must scan the sensing grid at a high refresh rate. This reporting rate is often much higher than the display's refresh rate, ensuring that the software anticipates your movement. This minimizes the input lag between your finger moving and the screen reacting. The controller IC is the brain of the interface, filtering out electrical noise and processing raw capacitive data into usable events. It must distinguish between a deliberate finger press and the chaotic electrical signals from the environment. This signal processing is the secret to a smooth touch experience. Multi-touch interaction creates a mathematical challenge known as ghosting, where the controller might misinterpret IK fingers as 3 or 4. Advanced projective capacitive algorithms resolve this by analyzing the intersections of the grid. This allows the machine to track 10 or more fingers simultaneously with absolute precision. One of the most critical software layers is Palm Rejection, which distinguishes between a finger and the side of your hand. By analyzing the surface area and pressure of the touch event, the algorithm ignores large, unintended contacts. This allows artists to rest their hands on the glass while drawing. For precision work, we use stylus technology, which comes in active and passive variants. Passive styluses simply mimic a finger, while active styluses contain their own electronics to communicate pressure and tilt. These professional tools allow for pixel-perfect accuracy that the human finger cannot physically achieve alone. In large public displays, we often see surface acoustic wave technology, which uses ultrasonic sound waves moving across the glass. When you touch the screen, you absorb a portion of the sound wave. This method offers incredible clarity because it doesn't require conductive layers over the image. Infrared touchscreens use a grid of LEDs and sensors hidden in the bezel of the monitor. When your finger approaches, it breaks the invisible beams of light, alerting the controller to the position. This technology is rugged and can be added to any existing screen without adding internal layers. Some high-end interactive boards use optical imaging, utilizing small cameras in the corners to track shadows. By calculating the triangulation of the shadow cast by your finger, the system determines the touch point. This works with any object and is popular for massive, wall-sized collaborative displays. Force Touch and 3D Touch introduced a third dimension to the interface by measuring the pressure of the press. This is achieved through strain gauges or by measuring the change in capacitance as the glass slightly deforms. It allows for deeper software interactions based on how hard you press. To improve the tactile feel, manufacturers apply an oleophobic coating to the glass surface. This oil-repellent layer prevents fingerprints from sticking and allows your finger to glide smoothly. Additionally, anti-reflective coatings reduce glare, ensuring the screen remains usable under direct sunlight or harsh indoor office lighting. Despite their sophistication, capacitive screens struggle with water and electrical interference. Water droplets act as conductors, confusing the sensing grid and creating erratic touch events. Modern engineers use advanced filtering and waterproof algorithms to help the controller distinguish between a wet finger and a raindrop on the glass. The final manufacturing step is optical bonding, where the display and the touch sensor are laminated together using a vacuum. This removes the air gap between the layers, reducing reflections and improving the structural strength. A well-bonded screen feels like you are touching the pixels directly. The evolution of touch has set the stage for even more complex sensing technologies that allow our devices to understand their orientation in space. In our next instructional lesson, we will explore sensors, specifically gyroscopes, accelerometers, and GPS. We will explain how your phone knows exactly which way it is tilting.
High-end capacitive glass remains the industry standard for consumer electronics, but specialized resistive screens still dominate industrial and medical environments. The choice between these technologies depends entirely on the specific environment and the requirements of the user. Considering your daily usage, do you prefer the glass-smooth precision of capacitive screens or the pressure-based ruggedness of resistive touch? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.